let me begin with some code that I had sent you. All right, so what I'm going to do here is uh, uh, I will basically we looked at certain concepts yesterday. We said, say we have a random variable x, all right, and we take a sample out of this, okay, and let's say sample size is n, sample size is n, okay, and let's say that this population, this is a population distribution. Let's say x is taken from so x is a sample that I've taken of size n from a population. Let's call it p. All right. So I've taken it from p, capital P, not the small p. Okay. Now this population p has a mean of mu. Let's call it mu, and a standard deviation of sigma. Okay, so I take a sample of size n, okay, and for this, say, let me call it x. All right, so the sample, let me call it x. If I was to take the mean of this sample, let me call it x bar. All right, and the standard deviation, let me call it s. What can I say about them? Would they be exactly the same as mu and sigma, or would they be any different? Can I say can I identify some properties about x bar and s? What is it? Okay, so first thing that we saw yesterday is that, so basically this x bar is approximately close to, x bar is approximately close to mu, but not necessarily exactly equal to mu, right? And if I was to keep on taking such samples, let's say I keep on taking such samples, I will have some distribution. It's a distribution of x bars, right? So that's why I say the capital X. Okay, so let me call this small x. Okay, and then the small x distribution, let me call it a capital X. So many such points. Okay, so this distribution has a normal. It tends to become a normal distribution. Okay, irrespective of what distribution the population has. Okay, and not only that, it will tend to become a normal distribution such that its expected mean of the mean, in a way, right? Expected mean of the mean would be something like mu, will be close to mu, and the standard deviation of this x bar, right? So it will have a mean and then it has a standard deviation. The standard deviation of the x bar is given by sigma under root of n. So basically what is happening is that, so effectively what is it? Effectively we're saying that x has to be actually close to mu, but it is not. And which means there is some error, right? So that error, how do I measure that error? So basically what is happening is, if suppose this is my p, all right, this is my p distribution, all right, and then if I was to take these x bars, right, and I plot that, the distribution will be something like this. It will be narrow, but at the same time it will be converging at the, whatever is the mean of p would end up becoming the mean of x also. All right, x bar rather, not x. Okay, so x is a sample out of it, x bar, and the standard deviation of the red one would be given by sigma upon square root of n. So this is what we want to, this is what we had learned, and this is what we call as the central limit theorem. Let's now do this in R. Let us simulate some numbers and do it in R. What we are saying is, let's say I assume that my sigma is equal to 1, right? And then I assume my n is equal to 5. And let's say I say my total number of simulations that I want to do. Basically what I'm saying is how many sample points that I want to take. So this x basically, right? So I say I take 50,000, all right, or 500,000 rather. And so I have all my x's. Okay, I say x dot all is equal to r norm. So I generate normal random variables, okay, with a mean of say 7 and a standard deviation equal to sigma, which is 1. And I also generate another one, which is again 500,000 data points with a mean of 10 and a standard deviation of sigma, which is equal to 1. What I do next is, So far is it clear? Let me just execute this for you. Let me change my screen a little bit. Okay. So I'm going to execute these lines of code. So I'm executing the line number up here. You may also want to open this file. Okay. So I've created the XOR and the YOR. So once I have that, so now XOR will have 500,000 data points. I'm converting it into a matrix. So basically I had a single array. All right. So the single array, I'm converting it into a matrix by picking up the data points. What am I doing? I'm picking up 5 data points first and I'm putting them in one row. All right. So basically 5 columns. Okay. Then the next 5 data points, I put them here like this. Next 5 data points, I put them here. So on. So basically I will have 500,000 I had total points, right? Divided by n. So I get 100,000 rows. All right. So, and for each of these n, that is 5 data points that are there, I would take the average. So basically, if I go back here, I have a sample size of 5 and I get my small x bar, right? But I keep on getting this small x bar for 100,000 times. All right. So basically, I get my x bar distribution. Okay. And I'm going to plot the distribution and see what happens. Okay. So this is what I'm doing. So I create a matrix first and then I take the means of it. Row means is a function which will take the means of the rows. All right. So I get another array which is x dot means, which is the row. Similarly, I'm repeating the same thing for y. All right. And then I plot it. Let's see what I get. So how am I plotting it? I'm saying typically what happens is when you plot a normal distribution kind of a curve, it will have a height which is about up to 0.4. All right. So I'm just multiplying it by square root of n. I will tell you what the reason is, but for now I'm just doing it this way. And then I'm taking the x limit from 0 to 12. Okay. So this is what I'm plotting. Okay. I'm plotting the x all. Okay. And then I'm also plotting the x means. Let's see what happens. So, so I say I create the matrix and I take the means of the data. And then let's plot. So this is what we get. So as I plot it, so this is visible to you guys. So I plot x all right. So I'm plotting x all here, by the way, all the data points that I had. Okay, how do I plot it? There's a function called density. Density will convert it into a density curve. So instead of using hist for histogram, this is an even better curve, right? So if you see, it's a normal distribution with a mean around 7, okay, and standard deviation 1. Okay, next thing that I'm going to plot on the same curve, on the same diagram is x means. And suddenly we see this. So what has happened? Because we know that the area under the probability density curve has to be equal to 1. And now this is getting divided by square root of n, right? So which means that my standard deviation was 1. Now it becomes 1 divided by square root of n, which is roughly 1 divided by 5, square root of 5. And that's why I get this. If I was to increase my n, I would keep on getting a different value. Let's repeat this with an n of 10. Okay. So I'm just rerunning this much of code. And you see that it becomes slightly narrower. Not so much difference which is visible. I'm doing it for n equal to 100. Okay. So I take it up and suddenly you see it's much narrower. Right. And but by the way, you see that this has reached all the way up to 4. So, and this has become smaller. Basically, this length has increased. That's why area under the curve will still be 1. Is this clear to you? Yeah, I'll come to the mean of means, Anmol. Just give me 1 second. Okay. I just happen to see your question just right now. Maybe let me switch on your mics. Okay. But make sure that you don't keep any, don't do any cross talking. Okay. So that way I will, so I've switched on the mics. Is somebody?
I got it.
You got it, no? Okay. Is somebody amongst you using the laptop microphone? Because that would tend to create more noise. I think that's noisy. Shall I shut down the? I'm going to, okay, wait, I think this is clearer. It's too noisy for me to keep it that way. I think we need some kind of a, disruption, because for example, Anmol had a question and I was continuing to look at my screen. So I missed out on what question he had. Okay. Uh, anyways, so yeah, but yeah, so you can do that, right? So raise hand when you have a doubt. Okay. Uh, but I would want some sound that comes out, it'll be even better. So ideally this software should have a, is there a way to kind of, I get some beep, which allows me to understand that there's a question that has been raised? I don't think there's a way. Anyways, let's move ahead. So is this clear to you? Have you understood? We were talking about this concept, and we can actually see this concept happening in the code here. Yeah. Okay. Yeah, Lavita, you've got a question. Let me give you my mic access. Yeah, go ahead, Lavita. You can speak through the mic. I would have expected that you've said it right today. I don't get any notification. I mean, I don't get any pop-up. It just shows up as a hand in the, yeah, like for example, Lavita raised the hand. So only if I'm looking at the control panel, I can see that the hand has been raised. Otherwise, I don't get any kind of a, pop-up happening on my screen. Ideally, if that was happening, it would have been easier. Are you asking me or are you telling me? Because there's a question mark at the end, but yeah, no, I don't get a notification. All right. Okay, so is this thing clear so far? If it is clear, just raise your hands. What has happened here? Okay, Lavita, it is clear. So Preet, yeah. Anmol may be slightly new for you in case you didn't watch to the Kameshwar. Okay, Dipankar, Anmol. Pratik is also there. Pratik. All right. Pratik, it is clear. Dipankar, not clear? Okay, fine. So let's move ahead. So I'm doing the same thing now for, so let me just plot it. I'll do it for simplicity's sake. I'll do it for n is equal to 10. Okay. So I do it for n is equal to 10. And I have my curve coming up here. All right. And then I do it for y as well. Okay. So here's my y. Initially is just the curve. So I get another one, right? Look, this black one is for x, and the other one that has come up is for y. All right. And then I plot the means curve on this. So this is what is there for the. So we have. So this line is, you can say, the population 1, this is population 2, rather this is the sample. This is x, this is y, and this is x bar, capital X bar, and this is capital Y bar. All right. Now what I do is, next is I take the difference between the two. Remember, yesterday we also talked about the concept of saying that if we were to take a difference between the two, wherein I say x minus y, all right. So if I was to take x minus y, then the mean would be equal to mean of x minus mean of y. At the same time, the variance is given by variance of x plus variance of y. All right. So let's look at that. So we know this mathematically. So what I'm doing is I'm plotting another curve now. So here is my curve. Okay. So I'm plotting a curve which is the difference between the two. If you notice this light gray line that has come up, it is what? The difference between the two. And if you notice, it is broader than the previous ones, which means the variance has increased, right? At the same time, it is centered around 3. And that's what is what it anyways is supposed to be. Just a second. I've made some changes. Guys, can you just somebody raise the hand, and I want to see if I get a notification or not. I have kind of collapsed my, Excellent. So there's a way for me to note that. All right, perfect. So this works fine. Good enough. So if do you see what has happened? So this is the gray one is x minus y. All right, and the next thing that I take is the difference between the means also. So if I straight away take the difference between the means and I plot that, so amazing. So I get that straight away. All right, and it would probably be the same as if I was to convert y minus. So if I was to go by taking the means of y minus x all overall. All right. So and then what I'm doing is I'm calculating the variance of x means minus y means. Let's see what I get. At the same time, I'm also using the, so mathematically, I should get the variance as 2 into sigma square by n, right? The variance of the green one should be what? 2 into sigma square by n? Is this correct or not? And what will be the variance of y all minus x all? Let's look at that as well. I say variance of y dot all minus x dot all, and I want to compare it with 2 into sigma square. All right, because there'll be, so let's look at this first. What do I get? Notice here 2.00, that is what is from the simulated data, and 2 is the theoretical answer. So they are close to each other, right? Similarly, now I want to take the variance of the means of the two data and the difference of the two, right? So if I take that, wait, I made some mistake, I guess. So I get three values here. What are these three values? So one is the x dot means minus y dot means variance, all right? Given that n is 10, right? So n is 10, so I get 0.2. All right, why am I getting 0.2? Yeah, right, so it's divided by n, right? So 2 divided by 10 gives me 0.2. Similarly, mathematically also, I get 2 into sigma square by n, which is again 0.2. At the same time, I'm also taking the, wait, so this is not the correct thing here. Let me delete it, okay? It doesn't make any sense. So only this much. So is this clear? So mathematically also we're getting the same result, and from the simulation also we're getting the same result. So what did we do here? We pulled out x. We took a sample set which is x. Then we took a sample set which is y. From this we created x bar. From this we also created y bar. So there was these two distributions and these two distributions. We had four distributions. Two distributions here, two distributions here. All right. Then we created another distribution which is x minus y. All right. And we also created another distribution which is x bar minus y bar. All right. And for all of them, we noticed that our fundamental rules about variance are being followed by, and they are in comparison with what we should be getting theoretically. So theoretically, x minus y would give you a variance of x plus variance of y. Right? Similarly, x bar minus y bar will give a variance of x bar minus variance of y plus variance of y bar, which is sigma x square upon n plus sigma y square upon n. Right? Because in this case n is the same, and in this case because sigma is also the same, so it comes out to be 2 into sigma by n. Right? So have you understood it so far? Everything? Wait, you seem to have a question there. Where sigma of x and y should be different, then how can two? Oh, wait. In this case, we assumed both the sigmas to be 1. If you notice, when I created x and y, I said the mean is different, but the sigma is same. 1 and 1. Right? So, in fact, this was a simplistic case. We are going to look at the more complicated one as we move ahead. So, Anmol, have I answered your question? Yeah? Okay. So, let me again ask you this. Are all of you clear with what we did here now? Because I'm going to, now next thing I'm going to do is I'm going to change the sigma. I'm also going to change the n. Why variances are added, that's what we covered in the class yesterday. Variance tends to be the square of something, right? So if it is a square, even if it's -1, right? -1 into square will become 1. So that's how it ends up getting added. Intuitively, when you're talking about any data, right? So the variation will become more if you add or subtract anything else to it, right? So addition or subtraction doesn't make a difference because there is randomness to it. All right. So that's the reason. So variance will always get added, means will always get subtracted or added depending on what is happening. So this is the fundamental thing about variance. Okay, so we yesterday's class we covered that only. Okay, now what are the changes that I want to make? So in both cases I took normal distribution, right? Let's say I want to say different n and different variance. So I say sigma 1 is 1, sigma 2 is 2, n1 is 5 and 2 is 10. Okay, then I'm taking a total, but this time total is not because finally it's total number of rows that I'm interested in. Okay, rows of x1 and y1. So what I'm doing here right this time is, okay, so I have x and y. Here I have my sigma is equal to 1, all right, and here I have my sigma is equal to 2, all right, and here I'm taking a mean of 7, here I'm taking a mean of 10, all right, and then I'm saying my n1 here is 5, n2 is 10, all right. So I'm drawing this from some population which is having this characteristics. This is the population characteristics, all right. So this is to do with py, population of y. This is to do with px, population of x, all right. And then this is the sample size from this population that I'm pulling, which gives me x, all right. So now I'm creating x and I'm saying I'm interested in x bars. And how many x bars? I'm saying 50,000, all right. And similarly I'm interested in y bars and I'm saying I'm interested in 50,000. Okay, so to create 50,000 x bars, how many data points will I need to pull out? Into n1, right? Similarly here, how many data points will I need to pull out, or samples will I need to put into n2, right? So that is what the change is here. So I say 5,000 into n1 and so on. So I get another set of x and y, and then I create a matrix just like earlier, and then I take the means of it. So the number of data points in x means and y means will be the same, whereas the number of data points in x dot all and y dot all will be different, right? So let me execute these many lines of code and let's see what we have. Okay, and then I'm plotting x. So I get this, which is just like what I had last time. And then I'm plotting x means on top of this. So I get this, all right, fair enough. And then I'm plotting y. Okay, now y has more standard deviation, therefore it's going down flat like this. And then I'm plotting the means out of it. So all right, I get this. Now next thing I'm doing is similarly I do y all minus x all. Okay, what do I get? I get another variation here, all right, distribution here, and then I do y means dot x means, and I get something like this. Okay, so mathematically then we have to compare this now, right? So first thing that we do is similarly like we had the previous case. Let me pull up this formula from here. So variance of this, the gray line here, is what I want to compute, all right. And then theoretically this variance should be equal to what? Sigma 1 square plus sigma 2 square, all right. Let's see if this holds good. So if you notice, the answer that I got is 4.99, all right, when I use the simulation, and 5 when I use the theory. So which means this is correct. It's holding good even for the cases where n is different and even the standard deviation is different and even the mu anyways is different. But the only thing common is that both of them are normal distributions. Fair enough. Let me apply the same thing for uh, so I'm computing three calculations now. One is yeah, another interesting thing that I will tell you here now. So I'm getting three values here. By the way, the first value is variance of x dot means minus y dot means. Okay. Third value is just this value, but then I've divided by n1 in this case and n2 in this case. And then another one is I'm taking the standard deviation of x. All right, what is x? X was known matrix. All right. So wait, let me do x dot all. Right. So I'm doing three computations here. Okay, and all of the three seem to be exactly almost the same with an error of maybe just a few uh, uh, a very small error or in the okay. So let me just put it here, it'll be easier for me. Okay, so what are the things that I'm computing here? If you notice, one is based on the first one is x means dot y means, which is based what I'm doing. I'm saying x bar minus y bar, okay, and I'm actually calculating the variance. So I'm using the variance formula here. All right. So this is from the simulations, and then I'm using a little theory. I'm saying based on total theory, what should this answer be? It should be we know that finally uh, uh, we know that the x bar will have a variance which is given by sigma square divided by n1, right? And y bar is given, so therefore a plus here because I'm subtracting the two. So sigma 1 sigma 2 square by n2. So this is purely theoretical, all right? And I'm getting an answer of 0.6 exact, all right? Now, third thing that I'm doing here is I'm saying, look, what if I compute this standard deviation, right? So this is what I began with. One is what I began with, two is what I began with, right? What if I compute the sigma? How do I compute it? I pass the data. What was my original data? It was x dot all, right? So x dot all, I compute either the variance of the standard deviation. Let's say I compute the standard deviation, right? Based on what data I got. And then I square it up. And I divide it by n1. Similarly, I compute the standard deviation as a standard deviation of y dot all. Okay? And I get n2. And I get this answer also very close to 0.6. I get 0.598. So there are three things here. What is this called? This is the sample. So this is the standard deviation of the sample. I denoted by S. So this was sigma. This is S. So I'm saying S1. So please understand the difference between the sample standard deviation and the population standard deviation. So this is sample. This is population. So is this part also clear to you? All of you? Because this is something very, very fundamental. I mean, these small things, you have to be clear about. So there is a sample there, and I have a sample variance, then I have a mean from the sample, then I have the means variance wherein I compute the n, and then I have the theoretical calculation, right? So all of these numbers come comparable to each other. Now what I'm doing is, let me just reduce the size. Let's see what happens, right? I'm going to make the size have I ended up changing something drastically? So So instead of 50,000, I make this my total size really small. I just make it 500. All right. And let's do the same computations again. And let's see what we get. So this time I get an answer which is 0.569, 0.6, 0.594. So the first one is not so comparable, but the last two ones are still comparable. Previously I had got an answer which was much closer to 0.6. Do you see this? So as I reduce my sample size, naturally I would have more variance and larger chance of error. Is this clear also? So how the sample size also impacts the answer. Okay, so now this time what I'm doing is, what did we have? We have both x and y as normal distributions. So what I'm doing is I'm taking another distribution, not normal distribution. I'm taking uniform distribution. You know what a uniform distribution is? A uniform distribution, typically we will draw it and you will know. Okay. So I'm taking a uniform distribution. There's no concept of sigma 1 or sigma 2, but n1 and n2 still have a value, have a concept here. So I say n1 is 5, n2 is 10. And let me take a total of 500. Okay. So 500 into n. So instead of run norm, I'm using run R uniform, right? So I'm going through everything same, all right? And I'm plotting these two curves. Let's see, what do I get? So if you notice, the black one is your normal distribution. This is the plotting of it. Theoretically, it is such that at minimum value, that is 4, it becomes 0. At maximum value, again it becomes 0. In between 4 and 6, it will have a value of it will have a corresponding value such that the area under the curve is equal to 1. Is this fine? So and I plot, now notice one thing. When I plot the density curve, that seems to be something else. All right. What I'm going to do is, okay, let's plot the next one also. All right. So I plot the next one. This is coming up here. Okay, because it had a minimum of 7, maximum of 10. All right. So and so around 7, around 10, and so on. Okay, and then I plot the curve which is the mean of these values. But this curve doesn't seem to have the shape which is similar to uniform, and we don't know what is this, right? So but it definitely has a different shape. The next thing that I'm doing is I'm taking a difference between the two, y all minus x all. So I get something which is a flat line here, and then a kind of a trapezium, which is nothing but, if you look at this curve minus this curve, you'll get something like this. All right. So, and then I'm taking the difference in the density. So I get another curve here. This seems to have more variance, all right, than the blue and the red. So green has more variance than the blue and the red. Why? Because it is actually two random variables. Okay, and then I compute it mathematically. I'm going to explain this to you, don't worry. Okay, and apparently I get an answer which is close to each other. So I get 0.13, which is based on the simulation data, and then what is based on computation is right. So based on formula is more or less close to it. Okay, so know that the blue, the red, and the green curve are normal distribution. All right. If I was to increase my numbers, all right, let's make it 500,000. Let's plot it now. Let's see what we get. Okay. So what we're going to get here is more or less, you can't see this because it's really narrow, right? So, but actually the green one, the red one, and the blue one, all three of them are normal distributions. And this has become more clear to what the, so is it understood now? So we started off with again with x and y, and both of them were uniform distribution. So X and Y were samples, right? They were both from some population of X, and this was from population of Y, right? And both of these two were also uniform distribution. From this we created X bar, and from this we created Y bar, and both of them have normal distribution. All right, and then we created X minus Y, which has uniform distribution plus something else. All right, and then we created X bar minus Y bar, which has normal distribution, right? And our formula still hold true. So even though this was uniform distribution, this has still become normal distribution. Is this point clear to you guys? Have you understood this concept also so far? What is happening? Lavita, Kamishwar, Supreet, maybe just raise your hands if you understood this. Okay, Anmol, Dipankar got it. Kameshwar also got it. Lavita, Supreet. Is Lavita's machine hung? What is it? Supreet got it. Pratik got it. Pratik is sitting with Anmol, right? You didn't get it very clearly. What is it that you didn't get clearly? Okay. So is there a problem with the audio today? Is it? What's wrong with the audio? Not the execution part in R? Okay. Maybe what you can do is I have already sent you this code. You can go back and have a look at it. Yeah, you will need to do it on your own. Yeah, conceptually you guys are clear, which is good enough. Okay. So let me move ahead. So now what's the variation that I can make in this? The variation that I can make in this is that I say, how about comparing normal versus uniform, which means X is a normal distribution and Y is a uniform distribution. And then if I take X minus Y and X bar minus Y bar, what do I get? All right, still, so I'm having X dot all as normal distribution, okay, wherein again I take the concept of total into N1, okay, mean is 7, standard deviation is 10. And Y, what kind of data follows normal distribution? Are you asking me some real example? So yeah, uniform distribution. Are you asking me some real example of uniform distribution? Even I'll have to think about it. What kind of data will follow uniform distribution? Can't think of it. Let's just do a Google on this. Okay. So in fact, see, most of anything in nature normally follows normal distribution. Okay, so the distribution is key one in risk analysis. Says many Monte Carlo software algorithms use a sample for this from distribution. On the other hand, there are only a few real life processes that have this form of uncertainty. This could include, for example, the position of a particular air molecule in a room. Right. Signals? Yeah. And so, for example, position of an air molecule in a room, the point on a car tire where the next puncture will occur, right? The number of seconds past the minute that the current time is, length of time that one may have to wait for a train. In oil exploration, the position of the oil-water contact in a potential prospect is also often considered uniformly distributed. So all of these are uniform distributions, right? Examples of uniform distribution. So here, I'm sending you the link. Okay, so all right, so now what I'm doing is I'm taking X as a normal distribution. No, normal distribution is continuous. We never said it is, sorry, uniform distribution is continuous. We never said it is discrete. It's just that it is abruptly falling. It's falling abruptly. All right, so So I specify the min value and the max value. Okay, and based on the min value and the max value, just this is how I will draw it mathematically. But in theory, we have, when we simulate it, it tends to become like this. All right. So let's do a small uniform distribution here. I say random uniform. How many? Let's do 10. Okay. Min value is let's say 7. Max value is 10. Let's look at the values. So we would not get anything which is less than 7. Very unlikely, right? Or more than 10. Very, very unlikely. But we still can get, just like in our previous data. So if we increase the uh, size to 100, okay, and what we'll do is uh, we'll pull out any values which are more than 7 maybe. No, actually no. So there'll be nothing which is greater than 7, but everything will be close to these values. So discrete would be 7, 8, 9, 10 if the values are only 7, 8, 9, 10. But here we're getting all the values in between the, so from line from 7 to 10, any data point could be there. Is this clear, Lavita? Why it is continuous? It has abrupt end, but still the points are continuous. Like how many points are there between 0 and 1? Infinity, right? So that's how it is. Which one? The example that we looked at? In which examples? Is it in this example or the homework part that we're looking at? Uniform distribution, the way it is defined is not discrete. It's a continuous distribution. Let's open the Wikipedia for that. No. It is uniform distribution. It just so happens to be a rectangular distribution, but does not. It is not discrete distribution. All right. So here, let me send you the link. Okay. So that's how it is. Okay. Anyways, let's move ahead. So now the next thing is that we want to see one as normal distribution, another as uniform distribution, and compare the two. So I'm doing that in the code here. All right. So I'm generating everything. All right. And then I have control 3. So this is my old graph. All right. And then I create a new one. So this has got created. And let me just make it slightly smaller so it becomes more visible for us. And then for the x means, so all right, so this is where it goes. And y is my uniform distribution, but my means distribution would be normal distribution. Then I take a difference between the two. Okay, and when I take the difference between the means, all right, so both of them will be tend to be normal. Okay, and then I compare the variances. So I use the same formula, and again it works fine. Great, right? So notice that the formula for the variances, that is the central limit theorem, will still hold. Does not matter that your x was or y was coming from a non-normal distribution. Is this clear? So it doesn't matter what the distributions are. So is this concept clear to you guys? And I'll move ahead with some new concepts. So if it's clear to you guys, just please raise your hands. Lavita, it's clear. Kameshwar, Supreet, Anmol, Dipankar, Pratik. Okay. So this code I have already sent you. You guys can, play around with it and work it out and understand things better. All right. So having said that, let's move ahead now. The rest of you, there are any issues? Kameshwar, is it clear to you so far? Dipankar, it is clear? Acha, give me just a break of 1 minute. I need to drink some water. Huh? Okay. So, all right. So, shall we move ahead? Shall we move ahead? Raise your hands if that's fine. Any questions? Whatever we covered so far? Kameshwar, Lavita, Anmol, Pratik. Okay. So we noticed in all of this curves and everything that what were we really interested in? We were interested in saying that we have a population, all right, and this population has a mean and a standard deviation. Suppose we don't know the mean. What do? We take a sample, right? And this sample is, let's say, x. From this x, it has some size, let's say n, all right? Now I have a size n, and because of this size n, I can actually compute the mean. Let me call it x bar, right? Which is given by xi, summation of xi from 1 to n, right? Divided by n. So I get this as a mean, right? So x bar. Now x bar is supposed to be close to mu, but in reality it is not. And we just saw from all the previous examples that this x bar tends to have a normal distribution around mu, right? And we saw that the variance of this x bar is given by sigma square by n. Ideally, what is this? Even though it is the variance of this data, if we were to look at this data independently, it is for sure the variance of this data. But when we look at x bar in relationship with p, then what is it actually? It is the error, right? Ideally, we should get mu, but we're not getting it. So it's called the standard error of the mean, right? Mean because it was a mean value that we are concerned about, and we're saying it is standard error and not standard deviation, right? So suddenly we have a new terminology that we're using for this value. It is no more the variance or the standard deviation square. It is the standard error of the mean. Is this clear? So this is the terminology that is used, okay? And typically it is the terminology which is used for inferential uh, statistics. So wherever we want to infer something, we want to infer population, right? And therefore we will call it standard error of the mean. So coming back to our notes here. So we're saying standard error is the standard deviation of the sample distribution of a statistic. In this case, the statistic was what? The mean, right? So deviation from the population mean. So sampling distribution is what? The probability distribution of the given statistic based on the random sample. We have already actually computed this all. It may be considered as the distribution of the statistic for all possible samples from the same population of a given size. We have already done this in fact. Okay. So now, say for example, a population is normal distribution Random sample size, arithmetic mean, we have already done this. Okay. Uh, so similarly, we can have another statistic, say sample median instead of sample mean. Okay. And there also you will come up with some standard error of maybe the median, right? Just like we came up with standard error of the mean, we will say standard error of the median. So now standard deviation of sampling distribution of a statistic is referred to as the standard error of that quantity. And in our case, it is given by sigma upon square root of n. All right. So one important fact here is that provided that the samples are uncorrelated, which means they are independent, which is one basic assumption that we move ahead with, right? Sorry, I didn't notice that there was a hand raised. Okay, everything is fine. Any questions? Okay. All right, I guess no questions. So now what are we saying? So now the standard error of the mean tells me how erratic my computation will be, because I actually don't know mu. From the sample, that is x, I'm able to give some idea about the mu. Now if my formula is governed by square root of n, right, the standard deviation. So if I say that, so the implication is that my sample size, I need to make it 4 times to achieve half the measurement error, right? Because the measurement error is based on the standard error of the mean. So when I'm designing my statistical studies, where cost is a huge factor, so this may have a large role to play in understanding the cost benefit trade-offs, right? So I'm saying if I have to increase the sample size by 4 times, there's a lot of cost involved. Let's say you want to predict the election result, right? And decide what should be the size of n. Now the size of n, whatever it is, if I was to multiply it by 4 times, my cost of capturing the data becomes 4 times, but my result will improve only by half, right? Or only by 2 times. So I have to do a trade-off. What is that, right? Okay. So standard error, the mean versus the standard deviation. So this is typically, as we just saw the example now, it is for the random sampling process. Whenever we want to associate this data with the population, right? So it is normally for inferential statistics. On the other hand, standard deviation is a descriptive statistics. For example, if I was to look at each of you students, right? So your classroom, and say you have 107 students, and I say what is the score of a particular exam that all of you took, let's say marketing exam, right? And if I want to find out the standard deviation of that, now that standard deviation will be actually a standard deviation, it will be a descriptive statistic. It is not an inferential statistic, because it is not a sample of something, because I have all the data available to me, right? So this is not based on the probability theory, it's just pure mathematics, whereas this is based on probability theory and mathematics. So alright, so standard error mean tends to be 0 with increasing sample size, alright, whereas the standard deviation tends to population standard deviation with increasing sample size. So this is another thing that you need to understand, that as I increase my size, the standard deviation will tend to be the population standard deviation, whereas this will tend to become 0, because it is sigma square divided by n, whereas this is sigma, right? Let us look at some of the terminologies. I say mu is defined as the population mean, x bar is my sample mean, sigma square is population variance. Now sigma n square, what is that? Biased sample variance. Alright, so S is standard deviation, let's say, right? Sigma square is unbiased sample variance. Sigma n is my, I will come to this terminology of biased and unbiased. Sigma n is my uncorrected sample standard deviation. S is my corrected but still biased, not unbiased, sample deviation. Notice I'm using the terminology corrected and uncorrected and biased and unbiased here. All right. So we will look at this very quickly. What is this whole thing? I will not go through this maths part. Let's just look at this. So what am I saying? Say, for example, when I'm computing my mean, right? So now, so this is my definition of the variance. How am I computing it? I say compute x bar from this sample that I took, and from each of the values of the sample I subtract x bar, square it up, and then I divide it by n, right? Because I had n data points. But what is happening here is, how did I get x bar? I actually got x bar from each of these data points, that is x1 plus x2 plus x3 and so on divided by n, which means the total number of independent data points that I have, or the degrees of freedom that I have, is n minus 1, right? And no more n, right? So there's a long proof. I'm not going to go through this. In fact, you don't need to go through this. Basically, the whole of the proof in the end tells you that expected value of Sn square is given by this n minus 1 upon n into sigma square, which means my fraction that I need to take care of is n minus 1. So now what was I doing? I was saying sigma square by n, right? So now what I'll be saying is it's not sigma square by, so my samples variance, right, which is given by s square, I took it as this. But if I was to approximate it, because I don't know sigma is from the population, I can approximate it by so this is Sn, right, by s square divided by n minus 1, where is s square is the sample standard deviation. All right, so basically I'm not dividing it by n, I'm dividing it by n minus 1. All right, so that's the change that I'll bring. Okay, so intuitively, when population mean is unknown and a sample of size n is drawn from the population, then x bar, which is given by this, I've already spoken about it, and xi minus x bar is a residual of xi, right? So it's not the error, it's the residual. How much is x bar away from xi, right? So if x bar was actually mu, then it is error. But in this case, we can't call it an error. We really don't know which is the correct value, even because x bar is computed from those. So we have how many, so we get a residual vector which is x1 minus x bar and so on, right? And therefore we have only n minus 1 independent residuals, because the sum of all of these becomes 0, right? So and that's why we actually divide it by n minus 1. This is called Basel's correction. All right, so n minus 1 factor is Basel's correction. Now, three key things is that it does not yield unbiased standard deviation. Standard deviation will still be biased. Say if I was to say sigma upon n, sigma square upon n, right? So this is biased. I say s square upon n minus 1. This is unbiased. But if I was to take sigma for this, which is just the square root of this, it will have a problem. I can't take square root of n minus 1. It will again become biased. All right. So this doesn't work. So basically for that the correct factor is n minus 1.5. We don't do a proof of this, but the correct factor for standard deviation is this. All right. So this is just for you to know. We will not really use it much. Wherever we will use it, you will know. But at least understand that we have this biasness that is getting introduced. Okay. So the corrected estimator often has worse mean square error. Alright, so mean square error will actually become worse than the uncorrected one, and never has minimum mean square error. Different scale factors can always be used to minimize mean square error, as we said, n minus 1.5. So this is only necessary when the population mean is unknown. In case the population mean is known, then we don't have a problem. Is this okay? Alright, so 1 degree of freedom goes to sample mean. That is why we are left with n minus 1 degrees of freedom. Okay. So if the population mean is known, then there are n degrees of freedom to the sample variance. Otherwise, and then we consider xi minus mu, and it's called the error. But if it is not, mu is not known, then we take xi minus x bar, and it's called residual. All right. So the Basel correction is not applicable when we already know the mu. The estimate of population variance using sample mean will always be less than the population mean. So let's refer Basel correction wiki to understand this. Do you want me to go through this? I can point out to a very nice link, and it should be, it's very interesting to read through this, that why do we get it that way. All right. But I think we will deviate too much from what we need to cover in this course if we start going into the complete proofs of each of these things, right? Mathematical proofs. So let me just pull out the link and send it to you. Maybe just type Basel correction and you should get Wikipedia for that. So there's a very interesting proof here. Source of bias given by these values. Suppose that the mean of the whole population is 2050, but we don't know this, right? And how do we estimate it? We take a small sample. Let's say this is the sample 2051, 2053, 2055, 2050, 2051. So we compute the average. Our average comes out to be 2052, right? So now what am I doing? I want to compute the X bar. So this serves as an observable estimate of the unobservable population average, which is 2050. So now we face the problem of estimating the population variance. We don't know that, right? So that is the average of the squares of the deviations from 2050. If we knew the population average 2050, how would we compute it? We would say 2051 minus 2050 square plus 2053 minus 2050 and so on, right? And we get the answer as 7.2. But since we don't know that the actual answer is 2050, we end up using 2052. So we subtract 2052 from each of this and we get an answer which is much lower. We get an answer which is 3.2. So this is a much smaller estimate. Okay. So how do we solve this problem? So we can do it this way. Actually, it should have been this 2053 minus 2050. I can write it this way. I can say 2053 minus 2052 plus 2052 minus 2050, right? So once I do this and I square it up, right? So I get this term, an additional term here and a third term here. So what is happening here is this term is what I'm getting. The a square term is what I'm getting when I don't actually know 2050, right? That's what we saw here. And so basically we write all the 5 terms here like this. So this is because we have computed the mean. This is in case we knew the mean. Are you guys with me? Are you following whatever I'm talking? Please raise your hands if you're following whatever I'm talking. Anmol, Dipankar, Lavita, Pratik. Any questions? Voice is breaking. Let me just first send you the link. Okay. Is the net bad today? Is it? Is your net good enough or is it bad? Anmol, are you? Sorry, Supreet, are you there? Dipankar, you there? Okay. Pratik, you there? Maybe Anmol can type for Pratik in case he's there. Oh. Are you also, the rest of you are also facing the same problem with voice? Like Anmol is facing the problem. So I'm just trying to figure out whether the problem is from this end. Oh, Anmol cannot hear me at all. Supreet is also facing the problem. Oh, what's wrong? Now Lavita can. In case there is a problem from my end, how can I know this? Is there a way to check what is my upload speed and what all softwares are consuming my bandwidth? Is there any way to know what could be consuming my bandwidth, if at all? Though ideally it should not be a problem on my end. I think the Adobe Connect had an advantage that it used to use very little audio bandwidth. You could change it, but in go to training, net speed is fluctuating from your end, is it? Is there a way for you to monitor it? And can you also tell me any software through which I can monitor my net speed? Then just iStat. iStat apparently has a trial this thing, no? So do you have a crack for iStat? Are you guys able to hear me now? Each of you? Wi-Fi. So I'm getting this. How do I know what's my up speed and what's my down speed? Is transmit means what am I sending up? Is it? It doesn't tell me the breakup of things. iStat is the best actually. Just a second. So what's the scene? Still you can't hear me? So I have a, but it's not telling me which processes are using it. So I have decent, that's what I'm supposed to get also, about 700 kbps for upload. Download is huge. So anyways, I think on my end looks like it is pretty okay. Something is not okay at your end. Shall we proceed further? So now, all right. Okay. So now what we were doing here is we said, all right. So in case we did not know the standard, sorry, the actual mean, right? For example, 2050, right? And we only knew 2052. So what are we doing? We're using this terminology here. So a square, 2ab, b square. Now this is the additional thing. The sum of all of these entries will end up becoming 0. Okay. And we are left with a square plus b square. So if we're getting a square, the actual answer is more than a square. There's an additional b square also there, right? So that is the reason why when you divide it by n minus 1, you'll get a decent enough uh, so you'll be able to knock off this biasness. Okay, you'll kind of, at least to some extent, reduce it. All right, so that was just a little bit about the biasness part. Okay, uh, so coming back to our uh, class further. So all this is just the proof. So again, a uniform distribution, and we take an integral of that kind of thing and different things. So again, chi-square distribution, and fine. So what we'll do next is we will look at let me just see what all is there for us to cover in the. So introduction to variability, standard error of the mean we have taken care of. Variance data example, we've done that. Yeah, variance data example. Uh, let me just open the PDF, or rather what we will do is what do we cover now? Was it enough for you today? I can still cover another topic. I can start off and we can continue with another. Uh, my plan is to actually introduce you to the project part 1. Let me just actually read out what is there, right? We will at least go through what is the project and then we'll see what all is to be done about it. What's wrong? So let me just go to the assignment part. So it has two parts, the project. All right. Part 2 will you can do it only after we have covered all of the lectures in, I guess, even week 3. Okay, but part 1 we can cover even today. So I'm going to show you the part 1. All right, and I would like you to attempt it yourself. Whatever I have covered so far should help you to understand this, and I'll still run you through my code so that it becomes easier for you to solve this project. So what is he saying? In this project, we investigate the exponential distribution in R and compare it with the central limit theorem. The exponential distribution can be simulated in R using R exponent function with two parameters. One is n and another is lambda, where n is the number of data points that you want to simulate. And what is lambda? Lambda is the rate parameter, such that 1 by lambda is equal to the standard deviation as well as the mean. Okay, so for our case, we're going to set lambda is equal to 0.2. And he's saying you investigate the distribution for averages of 40 exponential, which means and then note that you will need to do 1,000 simulations. So what is he asking us to do? So first thing he's saying is that we have something called REXP. All right. So REXP will generate random numbers. Let's say I generate 10 random numbers, and then he's saying at a lambda at a rate equal to 0.2. All right. Uh, so I'm getting these values. What am I going to do? I plot it. Okay. So how do I plot it? I say plot density. Okay. So I get something like this. Instead of 10, let me plot more. Let me plot 100 data points. Okay, so I'm getting something. Let's plot 10,000 data points. So do you see it's an exponential kind of a curve? Yeah, you can relate to this curve. Basically, the value is reducing exponentially. It's like decay, right? Half decay kind of a thing. You understood the plot at least, how it goes? So what is he saying? He's saying that you want to plot this, but you want to plot such that you take the, again, just like we did it earlier, this time instead of using R uniform, let's use R exponential and see what happens. Okay, so let's come back to our code. So this was our code here. Let me pull up the last one, copy paste it. Okay, and see what we get. So copy pasted it. Let's make the necessary changes. We are only interested in one simulation, so it doesn't matter. Let's say our n1 he's saying is 40, right? Because he's saying that I want to take the size as 40. For simplicity's sake, I'll take both as n1 and n2 as 40. And then number of simulations he's saying is 1000. All right. And instead of R norm, let's do it for y. What am I going to do is REXP, right? I said REXP. Okay. And total into n1. And REXP has another parameter which is lambda. So let me define my lambda. I say lambda is equal to, sorry, what's the questions here? Let's look at it. So we say set lambda is equal to 0.2 for all simulations. All right, so my mean is going to be 1 by lambda. So lambda is equal to 0.2. All right, and then here I specify lambda. So this is how I'm generating my data here. All right, so let's run this. For simplicity's sake, let me knock off everything which is to do with 2. All right, let's just keep 1. So things are easier for you to understand. Knocking off anything to do with y. All right. Okay, so we just left with this much code. So we have n1 is equal to 40, lambda is equal to 0.2, total is equal to 1000. So I get x all, right? So let me knock off the sigma also. I just need this much. I create a matrix out of this, okay? And x is a matrix. And then I take the means, all right? And then I make the plot. So first plot is the x all, right? Let's see how it looks like. I do an x all plot. So this is what I'm getting. From 0 to 12, this is how it goes. Let's just change some things. I don't want to give a y limit. Okay, let's not give a y limit. Let's see what happens. All right, let's do a plot again. Yeah, looks good. Let's not give a x limit as well. All right, so let's see what we get. Pretty good, right? So this is what we got. The next thing that I want to do is on the same plot, I want to plot the means also. Oh, all right. So this seems to be going really high. So for that purpose, let me start giving it a x limit. All right, which is, so if you look at this graph, a maximum of maybe 12 or 13 is good enough, right? So I say C, I take it from -1 to 12, and then I give a y limit. I say y limit is equal to C 0 to 1. Let's see what we get. Okay, looks pretty neat. Very good, right? So if you see this, so now the black one is the R exponentials data, right? And the red one is the means data. Okay, so now let's come back to our assignment. What is he saying here? So we have plotted this, right? Now show that the sample mean, and compare it to the theoretical mean of the distribution. So what is the sample here? He's talking about the sample as, which one? Is it the R exponential or the means of the exponential that we have taken? Let's read it again. The mean of exponential distribution is 1 by lambda, and okay, you will investigate the distribution of averages of 40 exponential. Note that you will need to do 1000 simulations. So what am I investigating? Which distribution? The averages of the 40 exponential, right? So illustrate why so that's going to, the sample mean is going to be which one? Averages of exponential is what I'm going to be interested in, or the exponential values. So so graphically, is it the black line or the red line? You guys there? So theoretically, is it the black line or the red line? Are you all offline? How come I can't? I see Kameshwar is offline, Lavita is offline, Dipankar is offline, Supreet and Anmol are connected. Any of you there? Can you hear me? You guys there? What's wrong today? How? Oh. I see. Let me just give you guys my rights. Yeah. Hello? I've given you. Yeah. I have switched on the mics for all of you. What do we do?
Hello.
Yeah? Is that Anmol?
Yes, Bhaiya.
Yeah. Some problem with the audio, is it?
Yeah, I think some lag is also coming for audio.
What do we do about it? In fact, I see that the Kameshwar has just logged out, or rather, I see Lavita also offline. So looks like there is some problem with the transmission today. Oh.
We continue tomorrow, Bhaiya.
Yeah. It's already 11:15 anyways. Yeah. So, but good enough then. Fine. I think it's only just you there, right? Everyone else seems to have dropped out. Yeah. So
I covered the first lecture. Yeah.
Okay.
Yes, Bhaiya.
You covered the, sorry, fourth lecture means?
First lecture.
Okay.
I in sixth course. I was
Okay.
actually not in college. I was out of like I was in IMC representing for some competition.
Mm-hmm.
So couldn't attend the first two. So I attended the first class today, your YouTube video,
Okay.
and will attend the second lecture also tomorrow
Yeah,
because
second lecture is a little longish, but I mean, you can just do it on higher speed and just quickly finish it off, kind of thing, right? So, yeah,
right.
yeah,
I do that.
yeah. And I mean, this course is really, really very interesting.